Imagine that you're working for the Capital Bikeshare Program in Washington, D.C., and it's your job to figure out what the average demand is for bicycles at kiosks that are placed around the city. And so you collect some past data and you make a histogram of the past demands. And you find that the past demands are really quite variable, ranging anywhere from just a little bit above zero all the way up to over 8,000. Now, you don't know what probability distribution is responsible for generating this data, and frankly, that really doesn't matter too much to you. Really, what you would like to know is what is the mu parameter of that probability distribution? What is the expected value or average value of the probability distribution that's making the data? Now, if we go and look at some of the statistics of the sample, we find that the average value of the demand for each day is right at about 4,800 bikes, and the standard deviation of the number of bikes demanded is a bit over 1,700. So on any typical day, we expect about 4,800 bikes to be demanded, give or take maybe 1,700 or so. Now, how can we translate that into some sort of statement about the average value of the probability distribution that's making this data? Can we come up with a best guess for what that mu parameter is based on the data that we've collected, a guess for how far off we might be from the true value of mu, and can we come up with a confidence interval for the value of mu associated with this probability distribution, whatever it is that's generating the data? And so this is a pretty common task in business analytics. We don't know and don't particularly care what the probability distribution is that's generating our data. We just want to estimate that mu parameter, the expected value or average value of that probability distribution. So how do we come up with the best guess, an idea of how far off our guess might be, and a range of plausible values for mu based on the data values that we've collected? Now, the results hinge upon, I think, what's one of the most important theorems in all of statistics, the central limit theorem, and I think this is best illustrated with an interactive visualization. The central limit theorem is a statement about the sampling distribution of the sample average that we might observe when we go and collect data. So take, for example, the following probability distribution that's going to be responsible for generating the data values that we're going to collect. There's three possible values, x of 1, 2, and 8. They all appear with equal frequency. What possible values for the sample average might I observe as I consider samples of, say, size 10, size 25, etc.? If I scroll down just a little bit, I have the sampling distribution for when I'm dealing with samples of size 10. So if I envision all possible ways those sample values could have come out in a sample of size 10, maybe they were all 1s, maybe they were all 8s, probably some mix of 1s, 2s, and 8s, I can come up with a probability distribution on the sample average itself, the list of possible values that I might see from that sample average and their respective probabilities. And these vertical lines that I see on this plot show me the relative frequencies of the different possible sample averages that I might observe. Now, superimposed on this is a normal curve in red. That's actually what the central limit theorem has to deal with. But for right now, if we just look at that sampling distribution, we see that it has kind of a funky shape. There's some peaks, there's some valleys. There's very little that we could do to really describe what that overall shape looks like. And this is where the central limit theorem is going to come into play. What the central limit theorem says is that for a large enough sample, the sampling distribution of that sample average has approximately at least a normal distribution. So why don't I go ahead and change the number of data points in the samples that I'm envisioning? What if I look at all possible samples I could make that have 31 observations in it? So all 31 might be just all ones, my sample average would be 1. It might be all 2s, so my sample average would be 2. Most likely it would be a mix of 1s, 2s, and 8s. But if I imagine all possible samples of size 31 that could be generated, all the sample averages that I could observe and their relative frequencies, those vertical bars let me know what the sampling distribution of that sample average is. And it's still kind of got a funky shape. Overall, it does kind of look like a normal curve, a bell-shaped curve, but there's still peaks and valleys up and down below that red line. But what would happen if I increased the sample size even larger? What if I envisioned all possible samples I could potentially make by taking 100 values from this probability distribution? Well, in this case, if I imagine all the possible ways the sample could come out, all the possible sample averages I might be able to measure, and make a histogram of the relative frequencies of those possible averages, I now find something that looks astoundingly like a normal curve, that red curve that's been superimposed. And so here's what the central limit theorem has to tell us. It tells us that if we envision all possible random samples that could be generated from a probability distribution of a certain size, like 30 or 100, and look at a histogram of the sampling distribution of those sample averages, the list of possible averages I might observe and their respective probabilities, that histogram is going to look just like a normal distribution as long as the sample size is large enough. And the key fact is that it doesn't matter what the shape is of the underlying probability distribution that's making the data. This is always going to be a true occurrence. So if I were to go and change the probability distribution that's making the data, if I were to say, well, let's just generate data uniformly between, say, 0 and 15 in integer amounts, if I envisioned all possible samples of size 22 that I could make, look at all those possible sample averages and a relative frequency diagram of each one of those, I would find that actually for samples of size 22, the way the sample average might turn out is very well described by a normal distribution. Change that up one more time, maybe a very skewed distribution, peaking at 0, then slowly decaying off at larger values. For this very skewed distribution, the central limit theorem says that as long as I'm looking at a large enough sample, then the distribution of the possible sample averages is going to look approximately normal. Scanning down, I find that the sample average of size 22, if I look at the possible values of those, kind of looks like a normal distribution. There's a bit of a mismatch. But if I increase my consideration to all possible samples of size 100 that I might be able to generate from here, I would find that the overall shape of that distribution looks very similar to a normal distribution. If I zoom in really close, I'll be able to spot the differences. There'll be small differences between the histogram of those possible sample averages and that normal curve, but overall, it's a pretty close correspondence. And so, most important theorem in all of statistics is this central limit theorem, and it's a comment about the sampling distribution of the sample average that I might measure when I go and collect data. The sample average will, of course, depend on what particular set of sample values I happen to collect. The possible values for the sample average that I might measure is actually well described by a normal distribution with predictable parameters. If that underlying probability distribution is just f, I don't know what it is, maybe it's a log normal, maybe it's Poisson. But if that probability distribution has a mean of mu and a standard deviation of sigma, then the sampling distribution of the possible sample averages that I might measure is going to look very much like a normal curve with a peak at mu, the expected value or average of that probability distribution that's making the data, and with a standard deviation equal to sigma divided by the square root of n being the sample size, sigma being the standard deviation of that probability distribution that's making the data. And so it turns out that if I collect data, have a single sample, and I've measured a single sample average, I can actually predict how far off my sample average might be from mu, the expected value or average of the actual probability distribution that's making my data. And the central limit theorem unlocks this ability, and it's a very general statement. It says that regardless of the shape of that distribution that's making your data, this result is always going to be true. With that caveat is that we have enough data for the central limit theorem to be invoked. So the upshot is, if I want to estimate mu of whatever probability distribution is making my data, well, my best guess at mu is just the sample average x bar. X bar is going to be an unbiased estimator of mu. And I'm going to be able to predict how far my single sample average is away from mu just by calculating its standard error, that estimate of the typical difference between the x bars I might measure and the average value of the probability distribution mu. Now, to estimate the standard error here, well, the standard deviation of that normal curve of the sampling distribution is sigma over the square root of n, sigma being the standard deviation of that probability distribution making the data. I don't know what sigma is, so I also have to estimate that value. What could I use? Well, I could use the sample standard deviation to estimate sigma here. And so that's the way that we're going to define the standard error of the sample average, how far off we think that sample average might be from mu. We'll take our standard deviation and we'll divide by the square root of n. So for my bike demand data, I don't know what probability distribution is making the data, but I don't really care. I just want to estimate what the mu parameter is, the expected value of that probability distribution. My best guess is that sample average of 4,800 bikes. I see there's quite a lot of variability from day to day. The standard deviation of the data values is right at about 1760. So typically the daily demands differ from the overall average by about 1760 bikes or so. If I want to know how close my sample average might be to mu, well, I get that standard error. Take the standard deviation, divide by the square root of n, and I find the standard error is about 87. So my estimated average of 1800 or 4800 is likely off from mu, whatever the expected value is of the probability distribution making my data, by about 87 or so. So I've nailed down that by quite a bit. Now, armed with a great guess for what mu might be, armed with an idea of how far off my guess might be from the true value of mu, how can I come up with a confidence interval for mu? How can I come up with a range of plausible values for mu based on the data values that I've collected in the sample? Well, we're going to employ a very similar type of reasoning as to when we came up with the confidence interval for theta, the parameter of the probability distribution that we knew was making our data. So what we know is that the sampling distribution of the sample average is approximately normal, with a peak at mu and a standard deviation equal to sigma over the square root of n. And so one thing that we know about the normal distribution is that 95% of values are within 2 standard deviations of the peak. So the fact that the sampling distribution of the sample average, the distribution of the possible sample averages we might observe when we go collect data, the fact that it has that normal distribution means there's a 95% chance that the sample average that I'll go and measure will be within 2 standard deviations of the peak, within 2 sigma over the square root of n's. So it stands to reason that if I take my one sample average that I've measured and then go plus or minus 2 standard deviations away, 2 sigmas over square roots of n's, well, that would have an interval that has about a 95% chance of covering mu. And that reasoning sounds pretty good, except there's a twist here. The deal is, I don't know what the standard deviation is of that sampling distribution. It's sigma over the square root of n, sigma being the standard deviation of the probability distribution making the data. I don't know what that is. I also estimate that from the data with just the sample standard deviation. So there's a bit more uncertainty going on in this estimation procedure than we had when we were estimating theta using the MLE. I have to estimate mu with the sample average x bar, and I have to estimate sigma with the sample standard deviation. So maybe I need to go a little bit more than 2 standard errors away from the sample average to come up with a range of plausible values for mu based on my data. So how many standard errors do I need to go? Well, I need to figure out what's the sampling distribution of the number of standard errors that x bar is away from mu. And it turns out this is a very well-studied quantity. Back over 100 years ago, people had actually figured this out. And the name of this sampling distribution, the number of standard errors that x bar is away from mu, is known as the student t distribution. Now, the student t distribution has a parameter called the degrees of freedom, kind of a weird name for a parameter. That's its theta. And the size of the degrees of freedom parameter lets us know how wide that curve is. It looks like a normal curve, just a bit more heavy-tailed. It's a bit wider on the tails. So as we decrease the degrees of freedom, that curve becomes thicker and thicker, wider and wider. As we increase the degrees of freedom, the student t distribution resembles more and more a normal curve. So how do we know what the right t-distribution is to model the number of standard errors that x bar might be away from u? Well, it turns out that the degrees of freedom is just equal to the sample size minus 1. So that's great. We have an idea for how many standard errors, x bar, our sample average, might be from mu, and so we can take our x bar, move that number of standard errors away, and bam, there's our 95% confidence interval. So it's possible to get that number of standard errors that we need to move away from x bar with the qt function, kind of fun to say and fun to work with, if we ask for the correct percentile with the correct degrees of freedom. But since this is such a common procedure, we're just going to rely completely on t.test, t-test, to come up with a confidence interval for us. So if I want a 95% confidence interval for the average daily demand of bikes with that capital Bikeshare program, all I have to do is run t.test and throw in the data vector that contains those daily bike demands. When I do that, it goes ahead and lets me know how many degrees of freedom that t-distribution had, 409 in this case, the sample size minus 1. And it lets me know what the overall average was in the data, that 4,800, and we get the 95% confidence interval. I'm 95% confident that mu is somewhere between the range 4629 up to 4970 or so. So I have a range of plausible values for mu, the expected value or average value of whatever probability distribution I'm dealing with here that's generating this data based on the sample values that I've collected. Now, one caveat, in order for this procedure to go off without a hitch, we need to make sure the central limit theorem is in full effect, because we were using the fact that the number of standard errors, that x bar is away from the true value of mu, is a t-distribution, which in itself requires that the sampling distribution of x bar is approximately normal. So when is the central limit theorem going to be in play? Well, it's tied in actually to the sample size that you're dealing with. So, depending on your sample size, the shape of the histogram of your data values needs to look good. So, what do I mean by that? Well, once you've collected your data, you're going to make a histogram, and you're going to note if it's roughly symmetric, if it has a little bit of skew, or if it has a lot of skew. And the sample size that's required to invoke the central limit theorem is going to depend on this shape. So, if the shape of your histogram is roughly symmetric, good news is you don't need too many data values for the central limit theorem to be in play. About 10 or so, a dozen or so, and you're good to go. You'd be okay with making a confidence interval for mu in that case. If you look at your histogram and you see a little bit of skewness, well, you need a little bit more data for the central limit theorem to be in play. You would need at least about 2 dozen or so data points. Now, if you look at your histogram and it's very skewed, you're going to need a lot more data. The standard rule is that as long as you have at least 100 data values, the central limit theorem is going to be in effect regardless of what the shape of that histogram is. So if you find a really skewed distribution, you should have about at least 100 data points or so. Now, for the capital Bikeshare Program dataset, we were definitely in that realm. We had a total of 410 observations. So even though our histogram looks relatively symmetric, we're definitely good to go here. We really would have only needed about 25 or more data values for us to be pretty comfortable using the t.test procedure and coming up with this 95% confidence interval. We have way more data than what we need. And this is very often the result in business analytics. That's one of the great things about being in the field. Our data sets usually are really big. The central limit theorem is going to be in effect. Now, one thing you might actually see reference to when you open up a news article is not the standard error, the estimated average, but the margin of error instead. So what's the difference between standard error and margin of error? Well, the margin of error associated with the estimate is simply the half-width of that 95% confidence interval, the distance from the very center to the very edge of one of the sides of the confidence interval. So we know that we get the outer edge of the confidence interval just by moving plus or minus usually 2 standard errors away, whatever that t-distribution suggests. And so that's going to be our simple rule to translate between the two. That value from qt, the number of standard errors that we need to move from x bar to get our confidence interval, is always going to be right at about 2. Sometimes it's a little bit larger. But in general, the margin of error typically is just double that standard error. Now, one thing you're going to want to keep in mind, especially in business analytics, is whether or not you should be actually analyzing the average of the probability distribution at all. Because sometimes the average isn't really the most representative value that you might see in that distribution. So, for example, with this histogram, I've drawn a red line at where the average value is in this data, but that average value is noticeably shifted away from the peak. And so we have to ask ourselves, well, is that really doing justice to summarizing the distribution? Does that average really serve as a typical value we might see from this distribution? You might think it's totally fine. Other people might disagree. So what if we don't like this as a measure of a typical value? Well, I like working with logarithms of the values instead when I see a distribution like this. When I see a very skewed distribution of values, very often what I'll do is all my analysis on the logarithm of the values instead. So why is this advantageous? Well, if we look at a distribution of the logarithms of the recorded values, we see something really quite symmetric, which is great when it comes to doing the analysis in terms of a central limit theorem point of view. If we have a symmetric distribution, we need substantially fewer data points for that central limit theorem to be in effect and for us to get confidence intervals out than if we had a really skewed distribution. But if we were to go and measure the average value on the log scale and then unlog it by taking 10 and raising it to that average, what we would find is a value that is a lot closer to the peak, and at least to me feels a lot more representative of the typical value that we would see in this data. And so I'll leave that up to you. If you're dealing with a very skewed distribution, I don't think there's much harm in changing your viewpoint and saying, well, let's do our analysis on the logarithmic scale. Let's analyze the logs of these values instead, translate back to the original scale, use that as our measure of a typical value, etc. And sometimes, actually, you might want to come up with confidence intervals for the median of the distribution instead. If you have a really skewed distribution, the median value is always right in the middle of the distribution. There's a 50% chance of getting a value less than a median or greater than the median when we're dealing with PDFs or PMFs. And so what if we want to get a confidence interval for the median of that distribution instead? Maybe that's a better summary measure than the average. Well, in that case, you're going to want to read in some code that's in the .r file associated with this lecture. There's a function that I've written called getCI for percentile that allows you to come up with a confidence interval for any percentile of a distribution you have in mind. 25th, 50th, the median, the 99th, etc. So once you've read that function in, here's how to get the confidence interval. Now, the surprising thing is that the outputs and the inputs of getCI for percentile actually doesn't depend at all on the data values themselves. All you have to do is say how many data points you have, your n argument, and then what percentile you're trying to get the confidence interval for. P equal to 0.5 would be a confidence interval for the median. Now, the output of the function gives you something in terms of the sample's order statistics. It turns out that the best way to come up with a confidence interval for percentile is to look at the order statistics of your random sample. So sorting those values from smallest up to largest, and then using two of those values in that list as the lower and upper endpoints of the confidence interval. Now, in this case, I've generated 70 values, just uniformly between 0 and 1. I want a 95% confidence interval for the median. The output of the function says, well, take y28 to y45 as your confidence interval. In other words, find the 28th smallest value, find the 45th smallest value, and let the range of numbers between those two values serve as your confidence interval. And as a little FYI, that interval is going to have 95.3% confidence. It turns out that we're actually going to know the exact level of confidence when we run this command. With that central limit theorem, the double layer of approximations about normality, the sampling distribution of x bar, we're always getting that approximate 95% confidence interval out. Here, kind of nice, we have an exact level of confidence, a known level of confidence.